Okay. How's everybody doing? Tired for the day? Not yet. Okay. So I just wanted to check how many of you still haven't given me any your SSH keys, public keys. Okay. You've not yet.
No,
You're Rahul, right?
yeah,
Yeah.
I have given you the keys, but right now I'm not able to access it through my Git bash. Actually, it's showing me permission denied error.
Were you able to access it before?
No,
No. So you and Scott are together,
yeah,
right? So you have given it to me, but okay, I need to check. So you're team three, right?
yeah.
So let me check. Okay. But Scott is able to use currently. So okay, that's another question. How many of you got the VPN correctly configured? Requires some people had questions, right? Does everybody have VPN access now?
Yeah.
No, not yet. So you should try it soon. Requires I think two-factor authentication for your UIC account as well. So get the VPN ready, and once you log into the VPN, ideally, the best case scenario is that you should be able to just use the team at the rate of team, 1 2 3 4 5 6 7 whatever it is, at the rate of IP, in the same terminal where you generated the keys, especially the Windows people. Then you will be able to get onto the server. Okay. Um, so that's the server part. Um, so not much people. I mean, there's not much activity on the forums except for Jacob asking questions. So I would suggest start using this as a. Okay, this is some other. Okay. uh, Start using the forum as a base for your questions, right? Not just questions for course specific content. Maybe you can also give uh, content related to things that you're coming across online, for example. Anyway, so there's also a thread which I have, but you guys can also add in terms of what project ideas you want to pursue. um, Actually, some project ideas are somewhat easy given today's technology of what's available out there on GitHub and what other people have created in terms of packages. But some projects are also difficult. So it's good to talk to me or the TA to get idea of what to do. And and actually, let me complete that thread. So there's a uh, project that somebody in the industry pitched to me. So this project is about like working with GANs. So generative adversarial networks are basically, think of it as a black box from which you can generate new samples. So if there was a parametric model, let's say a Gaussian distribution, you know how to generate the samples. Just call numpy.random.random or something, right? But it's not Gaussian distribution in this case. It's going to be a black box which represents a distribution over real world images. Okay. So you can generate new samples, which means that images which are not in the data set but almost look real world like. That's the objective of GANs and things like that. So this project is about that. GANs are covered in each lecture. So we are currently in about still working with CNNs, but we'll get to GANs in about one, two, three more lectures. Okay. So you can potentially work on GANs as well if you want in your project, and if people interested in GANs, this is a good application area. But you don't. I mean, if you're interested, just let me know, and I think my industry contact can also jump in and kind of help you guys get started. Okay. That's with respect to project ideas. I'm also posting internship opportunities that I'm coming across. So if you also have some opportunities that you're coming across, you can post it there. Okay. Actually, uh, yeah, I mean internship opportunities and some other things. Okay, so you can look at them if you are interested. Uh, yeah, and then last point before I get into the lecture is yeah, so we will add, so there will be a minor change in terms of the project deadline. So there's of course a deadline itself, but we'll also try to have a mid deadline so that you don't start the project 1 week before the 1 week before the submission date, so that there's more feedback, continuous feedback. Okay, and so the assignment one is due. in 6 days, I guess 7 days, 6 days. So have a look at assignment one, those teams which have not started, same teams, okay, same project teams. You can work on these. Actually, you can work on them individually as well, but it's easier to work in teams. So, any questions about these logistical aspects? Okay. So, if not, then let's get to our um, goal for today. So last time we went into the details of like convolutional layer of a CNN, and maybe I didn't emphasize much last time, but convolution is just a matrix mult operation. Convolution is an operation. Uh, uh, it boils down to matrix multiplication with some input. Okay, but it's an operation found, I guess historically in signal processing area. It just means a slightly different. It's like an integration with a like a flip function essentially. Okay, in terms of signal processing, but we will not worry too much about that. Okay. For example, I don't know, some of you who have done signal processing or some related course, if you want to multiply two functions in time domain, you kind of do convolution of those two functions in the signal domain, in the sorry in the frequency domain. Okay. So there's some relation to signal processing in that respect. Uh, but anyway, today's goal, there are actually three modular parts. First part I'll go over quickly, which is just a recap of CNNs, and then I'm gonna talk about how to, at least I've collected some points of view to kind of poke into the CNN. CNNs or in general feed-forward neural networks have lots of weights, okay, and so it's very hard to understand whether the weights are well trained and so on. Other than of course the final score. So we want to, once you have a trained model, how do you kind of poke at it and to understand like what's going on? Okay, that's a few methods, and not just the methods that I'll present. There are many more methods, but I'll present some ways to understand what's going on in a trained model, trained CNN model. Okay, so that's the second part. So I mean, the second part is not written here, but okay, that's the second part. And then I'll come to transfer learning. Okay, and transfer learning is a very simple idea. So it's basically saying if you already have trained a model, then how can I reuse most of the model parameters and maybe introduce some couple of new model parameters and get really good performance in terms of classification in the new task. Okay, even if I don't have a lot of data in the new task. So that's transferring parameters. That's one of the goals. And I guess the goal that I just mentioned about poking holes at a trained network, trained CNN model, that's the second goal. And the third goal would be third and fourth goals are about additional things that you can do in with especially with CNNs. Okay, so for example, in CNNs you can also, there are a few tricks to stabilize the learning, as in it's a highly non-convex problem, so you want to get to the weights properly and not just get to wrong parameter values and so on. So there are some tricks. One is called batch normalization. The other one is called dropout. Um, those are the two key things that we'll see, and we'll also see one trick that typically people use for image data, which is called data augmentation, which is again a very simple idea. It's about, if you have an image, then just perturb it a little bit, shake it a little bit, and that's another example, another observation for you to train. Okay, so those are the few goals of today's lecture, and actually, how many of you could download that PyTorch basics tutorial and run through it? How many of you have actually gone through the PyTorch tutorial at all? Nobody. Okay. Uh, okay. Let's see. So I just. Oh, okay. What happened here? Okay. Okay. So let me actually. Where is this? So let me actually do in real time. At least show. Um, Spend some time on PyTorch for the first 15 minutes, because you'll see that that particular repo has a really nice example with just linear regression. Okay, so don't worry about neural networks. With linear regression, how do you deal with PyTorch? I mean basically the tensors in that package uh, and so on. So let me actually. Okay, so that's on the server side. Some teams will have access to this particular server. I mean, but I'm in my account, so what's it? Localhost, yes. I don't know if this is IP address, but let's try. Um, okay, 1000. Connection refused. Oh, 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 team 9. Okay, I'll not run it in a screen session, but doesn't matter for me, I think. Let's see. Okay, so notebooks. Okay, now I don't know which one is the first one. Okay, okay, let's actually. Let's try this. So let's see if this is the one. Yeah. So let me just. Okay, maybe. Basics. Sorry, I should have read the README file. Where is it? It's over here. Um, okay, guess for not need. So definitely go through all the notebooks in this repo. I mean, we are just gonna look at PyTorch basics, maybe even debugging, and linear regression for today. I mean, for the next 5-10 minutes. Okay, just so you understand the basic building blocks, because that's roughly what you'll see the same pattern again and again and again for the next 6 lectures, 6-7 weeks. Um, so basically, Torch is a package for doing. So what do these packages do actually? So Torch is one. PyTorch. I mean, as in PyTorch is one. TensorFlow is the other. MXNet, and then there's Chainer. Does anybody know anything else? What's it? Tiano. Yes, Tiano from yeah. So these are all packages which help you work with GPUs. First thing, okay. Uh, as well as the other thing they do is automatic differentiation. Okay, so the backdrop stuff that we saw in the first lecture, they do it automatically. Okay, so we'll see an example today, and so those are kind of the two biggest benefits. And internally, they do have this notion of computation graph. So we kind of did backdrop examples by hand, right? We drew like a graphical representation. That's kind of the internal representation that they also have. Okay, there are some differences in terms of the architecture of how they've been built in terms of software engineering, but for us, we are end users, so let's not worry about how the architecture of PyTorch is different from TensorFlow. Yeah.
So on the assignment, the first question is about the computation graphs.
Yeah.
So is there a preference as to using PyTorch over TensorFlow? Because I know
I thought the first question you can probably do it by hand, maybe.
do we have to display the computational graph by using some sort of library?
No, not necessary.
Because it says draw the computation graph.
Draw it, take a picture, and use Pillow or any imaging package to load it onto the notebook. Yeah, and save the notebook so that the image remains. Okay.
I was working on for 2 years, 2 hours yesterday on
Doing it.
TensorFlow.
No, but it doesn't say use TensorFlow, right? You could actually
No,
just
yeah,
use
but
Matplotlib to
since
plot.
we're submitting a Google, not Google, a Jupyter notebook, I thought we have to.
No, you can
actually
use a
plot.
plotting library like Matplotlib, but actually for graphs, you can use NetworkX draw.
I was able to do it with something called Dask.
Yeah, that's
Dask.
yeah, that's work too. Yeah.
What is Dask?
It's
It's a parallel scheduler, so that's why it's in computation graphs. You can see
Oh, it does draw the computation graph as well. Yeah, yeah. I remember that it's something to do with parallel computing.
the easiest one is TensorFlow, but the problem is it publishes it on TensorBoard, so
Okay.
you can't really display it on the notebook.
Yeah. Sure. I mean, first question is not an indicator of, there are later questions which are like actually need some coding. This question is just you can do it and do it by hand. Okay. So wait, where was that? So I was saying the key benefits are basically automatic differentiation. We'll see an example and access to GPU. Okay. So this repo is actually a little bit older from 2018. They might have updated it. You can actually refer to the official documentation, which is much more expansive and detailed. But so so basics, right? So here actually we don't need to import all these, but the most important things are torch.nn is where you'll get all sorts of layers. Okay, nn.module is a container where you can put different layers, like the CNN layer that we saw last time, pooling layer, or fully connected layer, and so on. And nn.function functional just is like stores functions like relu and softmax and so on. Okay, and maybe even the cross entropy loss function definition. So there's just a bunch of collections of functions. So you can actually look at the source to see what all is there in each one of them, each of these sub packages, I guess. Optim stores optimization techniques, SGD or gradient descent based methods, basically stochastic gradient descent, and there are some variations called Adagrad and Adam, which are popular. But we'll get there. We'll talk about them later. And torch vision is just a branch of for working with vision data as an image data. Okay, and pprint is like pretty print. So if you want to print arrays, if you want to have it nicer, then you can use this library. NumPy should be familiar to most of you. Start using it or try using it. It's basically very similar to people who have seen MATLAB before. Okay, or even like it uses a similar type of indexing like the data frames that you use in R also. Okay, so type of indexing that you have seen with data frames in R. And one of the key things is to use set trace. So people, in terms of debugging, okay, you will see lots of errors thrown out even on notebooks or whether you're using on command line with text files. There'll be a lot of errors. So you either use the usual, zeroth order thing, which is print statements. Okay, print out your variables before they're erroring out to figure out shapes and sizes and types and so on, or use debuggers. Okay, so IPython. So you can use a debugger on the Jupyter notebook. This is um, IPython debugger. Okay, and in particular they're using a particular function called set trace, which stops the execution and gives you control, so you can prod around and see what the variable values are. Okay, so debugger is very important kind of thing in programming. So since we are kind of stepping on the toes of programming area, so we should get to know the best practices. Okay, so anyway, let me run these. And also you should, I mean, I haven't really learned it, but you should learn the keyboard shortcut for using Jupyter Notebook. Okay, so Shift Enter to go to the next cell, create an next cell if it's not there, Control Enter to stay in the cell, Enter and Escape to do something inside the cell versus outside the cell, and add cells above and below and so on. Anyway, there's a keyboard, I think, command palette which will tell you. So let's get to. So here we're just importing some NumPy functions, matrix inverse function, and then matrix multiplication. Okay. So people must have seen this, right? So this is just identity function. I said identity matrix. So this part we've seen before. And torch.I will also give you an identity matrix. So now the type is a tensor type. So it's a little bit different. So it will have different fields which are hidden to us, but it will be useful for doing the like one of the most important fields will be like required grad, which if you set it to be true, then if that tensor appears in some computation graph that we'll see, like if the tensor is used to compute something else, then if required grad is true, then it automatically computes the gradient of the output with respect to that particular tensor. Okay, and I'll elaborate pretty soon about that. Okay, so random number generation. These are the two examples. Shape, asking for the shape of the matrices or tensors in this case, and actually don't care about all these, but let's move forward. Okay, inverse and so on. Okay. Uh, this is just how to add. You can actually just add by +1, but that's fine. So one important thing I guess I'll just note here is that you can add in place. So you'll see that what we'll do is these tensors that we created, as I said, the use of the package is that we can put this tensor onto the GPU. So in a sense, GPU will also have RAM. Okay, just like we have a RAM on the regular with the CPU here. So we can do in-place additions so that RAM on the GPU is somewhat, is not overutilized. Okay, so if you already have like a model which takes, has so many weights that is already taking 6 GB of memory, then you don't want to do non-in-place operations because then you'll kind of hit out of memory errors. Okay. Um, Indexing and broadcasting. I don't think I want to go into all those details. Uh, Yeah, and you can convert from torch tensors to numpy, and from numpy arrays to torch tensors. Okay, there are functions to do that. Um, okay, so this is the part where the GPU part helps. Okay, as I said, there are two kind of benefits for this. Going on to the GPU, doing automatic differentiation. The GPU is this part where, like, you can check if. So in this case, the author has written if Torch or CUDA is available, which means like it's kind of the library for interfacing with the GPU. Uh, if it's there, then the device will use that. Use that. In this case, there's only one GPU. So CUDA : 0 means the first GPU, or it has to be CPU. So you can see that the execution gave me CUDA as is there. Actually, I can do. I can actually just do. What is it then? So the command that I kind of use all the time. You can see that that's the GPU. It's using CUDA version 10 here. But one of the servers actually has an older version of the driver, so I will try to fix it soon. We'll see what happens with you guys. For I think teams 4, 5, and 6, I think the driver version is a little bit older for the same GPU. So I'll try to see if that needs to be fixed or not. If we can go ahead without changing the driver version, we can go ahead. Okay. Anyway, so now the cool thing is you can create tasks and tensors. When you create this, initially they are on the GPU side, okay, in the sense that the GPU and GPU's memory. So when you create a tensor, those 9 numbers, right, 3x3 matrix that you created, it's on the CPU side, sorry. And then when you do to device, okay, and if device is evaluated to the GPU, as you saw above, right? It's CUDA, which just means like that's the GPU. The device is going to be the GPU. Uh, then you can just do to device to push that particular data. So this data is just a placeholder for the tensor. So think of it. I have a tensor which I just created, which is on the CPU side. I can do to device to push it to the GPU side. Now the data is on the GPU. Okay. Now I can do some computations on GPU directly. Okay. It's going to be useful. So what typically you'll do is create, if you have data, push it to the GPU. If you have a model just means it's a container for a bunch of weights. Those weights are also tensors, so they're also essentially data in some sense, tensors. You also push that onto the GPU. So everything, all execution happens on the GPU. So the model, when you are training, the backdrop and gradients and optimization of the loss function, everything happens on the GPU side. Okay. So yeah, so that's the GPU part. That's a benefit of these packages, TensorFlow and PyTorch. And the second thing is gradients. Okay, so actually we don't need autograd, but let's see. So X is So we made a tensor, which is not a matrix here. It's just uh, it's a number. Okay, um, and then we can give not positional, but like a keyword argument. Required grad is equal to true. Then that type of tensor is created. So the difference between these two tensors is by default. Uh, I think requires grad is false. Actually, let me just check that. Um, actually, I executed the. I mean, now it's going to be true, but let's do this first. So by default, it's going to be false. Okay. So the tensors always come with this additional flag. Okay. And that's always false. So it doesn't compute any. I mean, it doesn't like do not backdrop. Doesn't compute gradients. Doesn't compute gradients by default. But if you do requires grad is equal to true, which is what you will do when you train a network. So when you instantiate a neural network, the parameters of the neural network will be tensors, and for those tensors, those parameter tensor, you will do dot require grad is equal to true explicitly if you want to. If you want to go to that low level, uh, PyTorch.nn will do that for you when you start when you instantiate a nn.linear, let's say linear layer. Then the linear layer will have some parameters, right? Simple fully connected layer will have some parameters, right? So those parameters by default, the required grad will be true. Okay, so that whenever it's involved in any computation, the local gradients for them will be computed in a forward pass. Okay, when forward computation happens. Okay. How many of you are not following what I'm saying? Is things a little bit clearer? I mean, this is not so that this is not a really short course on PyTorch. I mean, I just want to spend some time on it so that people are more comfortable. Um, we'll get to linear regression pretty soon. Okay. So let's actually on this. So x now explicitly gave requires grad is true. Okay. So and right now x's gradient is none because it was not used in any computation. So let's say y is equal to x squared. Okay. Oh, yeah. Even now, there is no, grad of x is not given yet. So gradients get computed when you do y dot backward. Okay. So I mean, the output dot backward will compute the gradients for any of the tensors for which required grad is equal to true. Okay. So if you wanted to do actually gradient descent, remember we first had to compute the gradients and then do the previous values, new value is previous value minus the gradient. Okay, so the gradient computation itself is achieved by for any output. So output will also be a tensor if input is a tensor typically. So any output it will always have a function, okay, which you can call on the tensor dot backward that will compute the gradient with respect to that guy, gradient of that guy with respect to all its inputs where required grad was true. Okay. So y was just a function of a single tensor x whose required grad was true. So when you did y dot backward, x is gradient. So gradient of y with respect to x was computed. Okay, and that you can see that the gradient of y with respect to x is 4 when x is equal to 2. Right. So it's the gradient of y with respect to x is 2x, and then x is equal to 2. It's 2 times that. 2 times 2, that is 4. Okay. And once you have the gradient, then you can use the gradient for a gradient update. That's not being shown here. That will be in an optimization scheme in machine learning. This is not in machine learning yet. Okay, so that you can do by calling optimizer.step or something like that. Okay, which will do just a gradient update. Okay, so yeah, and another trick is when you're doing training, you need gradients. But when you're not doing training, when you have a model, right? Remember, when we instantiated the model, by default the tensors have required grad is equal to true. Okay, and when so while training it's useful, but while evaluating you don't want the gradients to be computed. Okay, so there's way to kind of say that with torch.no grad do some computation, then even if required grad is true, the gradient is not computed. Okay, it's not ready to compute the gradients actually. Okay, so anyway, um, So that was with respect to two things: automatic gradient differentiation and GPU access. Um, and last thing is there's this module NN, which is a very handy module. I mean, you don't actually need to use NN module. You can actually write the whole your network from scratch explicitly as well as a composition of tensors, like function of tensors. Remember, like wx plus b, relu, and then wx plus b again, things like that. But there is a way to, I mean, there's prepackaged, I guess, classes from which you can instantiate these layers. Okay, so for example, here it's a linear layer with some input dimension, some output dimension, and whether you need to have b is equal to, whether you need to have a bias or not. Okay, so anyway, so that's basic. So go through that, and I just want to stop at the regression example. So again, so this first few lines are basic imports. We don't really need torch vision here. Maybe functional. We'll see if we'll not use relu, so we don't need that. Okay. Anyway, just starting all of them. So okay, the problem is, so here's a simple problem, right? So here we're going to make a one-dimensional regression problem. So the number of features is one. Okay, so just one feature, and 100 is the number of observations. And there's in scikit-learn. How many of you have heard of scikit-learn? Not heard? Scikit-learn. Scikit-learn is a really good, basic machine learning toolkit in Python. Just like I think Veka for, I guess, Java. I mean, I don't know what else is there in R. So Carrot or something. There are many different packages in each ecosystem. So scikit-learn is an example package here. It has many of these usual shallow models that you have heard of, like SVMs and random forests and gradient boosting machines. All of those are there. So you can use them. So here it's just a function call to create a fake or a simulated data set with number of samples you want, number of features you want, and some other keyword arguments. So let's run it and see how the data looks like. I don't think I have scikit-learn. Okay. So this is the data. Okay. One-dimensional data, x versus y. Okay. And we're gonna learn a linear model. In this case, it's just gonna be a line, right? That's what it should be. And we're gonna do that using PyTorch's tensors, and we'll do gradient descent. Okay. So first, what we're doing is converting those x comma y. So make regression. I mean, just think of this as x comma y is our design matrix, and the labels, not the labels, sorry, the dependent variables are the target values. So those are just numpy arrays. Okay, I didn't execute it, but those are numpy arrays, and I'm just changing them to torch tensors. Okay. Okay, that's the conversion. And why did I convert to torch tensors? Because now I can then push it to GPU if needed. Two device would push both the design matrix, the x's and the y's, to GPUs. And need it. Yeah. And here is a simple example of a linear regression model, which also illustrates typically the way people use build models in PyTorch. So you kind of extend the class from a base class called nm.module. Okay. So it's a very template-ish thing. So if you want to create any model, so here we are just creating a simple linear model. You don't have to do this. Okay, you can do it in a more simpler way. But this is kind of the things that you'll see even for CNNs, and even more later on RNNs, GANs, VAEs. All of them will have the same structure. Okay, even NLP tasks and all that. So the structure is you extend from a base class nm.module, and basically you have to create two functions. Okay, init function which creates the neural network. Okay, in this case, this neural network only has one. I mean, it's not really a neural network because there's only one parameter, which is a linear model parameter, beta. Okay, and so that is created using nn.linear with the input dimension of 1 and output dimension of input dimension of whatever is the input dimension. In this case, the input dimension is 1 because x's are one-dimensional data, right? And output dimension is 1. Okay, it's a regression problem, one-dimensional regression problem. And then you don't have to do this. Okay, you can actually do torch.tensor. Okay, and create a one cross one in this case um, tensor. Okay, that's it. And you can create the tensor and then do require grad is equal to true. Okay, that's what's being accomplished here. in nn.linear. And then the second function that you want to say is how does that model interact with the input data. Okay, so that's just so given data, in this case the design matrix, we are, I mean, we don't have to input the design matrix. We could always input the what is it, the each observation as well, but it's vectorized here. So all it's doing is here we are just calling self.beta. So self.beta is like sorry, beta is the name of that layer, in this case the linear layer, and so we're just calling the linear layer on the input. Okay, and it produces a one-dimensional output, and that's the output. So forward pass on this model is just saying I give an input x, I'll just compute beta times x and output that. Okay, that's what's happening. So okay, so that's the linear regression model, and then as I said, the nice thing about this, so this, uh, so if I call if I create an object from this class, okay, it's called model here, and here I'm actually creating the object as well as sending it to the device. Okay, as in like the model is so what is a model? It's nothing but a collection of tensors. Okay, it's just that the tensors basically model weights have to be updated using optimization. So it's just a collection of tensors. I'm pushing them to device. Okay, that's what's happening here. And then I'm defining what's the loss function. Okay, remember the first lecture, we just have to define what's the model, what's the loss, what's the optimization technique, and what's the data, right? So data we just created and pushed, we haven't pushed it to device yet, but this is the data. Model, loss function, and optimization are these three lines. Loss function is just a square loss, and optimization in this case is just some choice, in this case stochastic gradient descent, SGD, but there could be other subroutines, and you'll have to look up their APIs, their function signatures. And I'm sending the data to device as well. Okay, so I let me just okay, so we send it to device. And if you really are not sure if it really went to device or not, you can do NVIDIA SMI to see if the device memory was actually consumed. That's a very easy way to see that, yeah, some data went to the device. And then yeah, and then here is one step of gradient descent step. Okay, so in the sense that you can put this cell into a for loop to do the gradient descent again and again and again. But here, for simplicity, we're just showing, okay, what are the steps needed. First of all, model or train, I think don't remember exactly what it does. I think it just makes the what does it do?
It initializes the, so it's kind of a function. So you call it again, and actually it's just an initializer for training.
Yeah. I mean, I'm just saying it's some simple step. I think it's something to do with required grads or something. Don't remember. But anyway, there's a difference. So you just check what model.train and model.eval do. I think they just either enable or disable the gradient computation, which automatically happens, right? Anyway, so optimizer zero grad is something that you should do in every step of your optimization. Okay, it just clears out the gradient information in any of the variables. Any of the the weights will have the local gradients, right? So the gradient that were computed from previous step, they should be set to zero. And then now we're just taking model forward pass. So model X is the forward pass. Model was the object from the class, remember? So I gave the data, which is already on the GPU. Model is already on the GPU. So Y is the output tensor, and then loss is being compared with the output is being compared with the true data, which is also on the GPU, and uh, in this case, loss is being computed. You can actually do this manually, okay, and literally explicitly write what the mean square error is and compute the loss. And remember, loss. So loss is the final tensor. Okay, so from input tensors, these two, finally some tensor called output. Okay, it's one-dimensional number. Now we're just asking loss dot backward will compute the gradients with respect to the model parameters. Remember the nn dot module. I mean, the model had a linear layer, so there's one beta actually. So we'll just compute the gradient with respect to that beta, and then optimizer dot step is just doing that one step of gradient descent update. So in this case, stochastic gradient descent, it just says beta old minus some learning rate, which I think I chose to be 0.001 times the gradient of loss with respect to beta. Okay, it's just a one-dimensional example, so it's easy. And then I mean, ideally you should not do this, but here we are just evaluating how does the model perform on the training data itself, on the data that was used for um, uh, the training step. Okay, so I mean, this step would be for a separate held out data set. So typically, you'll see that in these workflows, you'll not really do cross validation. So there's only just one train set and one validation set. It's just that the validation set is always used to report the numbers, and the train set is used to just train and fix the parameters of your network of your model. Okay, so unlike cross validation that you've seen in shallow models where you would have you would always split into multiple folds. Some folds are used for training, some fold is used to report numbers or evaluate the quality of the model and so on. So here there's only one held out validation set, and that's the part that you should do here. Anyway, let me execute this. So you can see that the model is quite bad right now. So this is one step. Okay, so okay, it's not really working. I mean, you can see that in this case they are reporting the mean square error at the top, and it's not really changing. So let me go back and decrease the learning rate. I mean, sorry, increase the learning rate. Yeah. So, okay, some reduction. You can see that MSE is reducing to, and you can see grain descent. All it's changing is the beta, and beta is just the slope of this line. So it's just turning this to. So that's essentially what is the architecture for majority of the classification regression problems that you'll do. I'm not going to spend more time on this. Anyway, any questions about this? So I hope after this you guys should go ahead and try out PyTorch. I mean the tutorial, at least on Colab, if not on the servers. Okay, and get more familiar with PyTorch. Yeah.
How do we define device in the code?
Two device.
Yeah, this device, where do
We did it right somewhere. This one.
we go?
I mean, it's just a torch.device. I mean, it's just yeah. This is literally just remember this or copy paste this.
Do we have to always do it on any device if on a collab?
What is it?
Do we have to always run that?
Yeah, run it. It's fine. I think if you run it on Collab, I mean, as long as the Collab, your notebook has access to the K80 or whatever the GPU is then it will set it to the GPU and use CUDA. Yeah. If you don't run it, then by default all the computation will be happening on the CPU. Yeah. Unless it's being set somewhere else in your script, then this is what you should be doing. Okay. This is the bare bones. Actually, most of the stuff you will probably not see explicitly. But any questions? Yeah.
So the main advantage of this PyTorch
Yeah.
is that it allows you to run it on the GPU. Is that right?
And does backpropagation for you. Backprop stuff that we saw in the first lecture. Yeah, those two. And another nice thing that the author says is that there is, you can actually use settrace, the debugger that I kind of showed you, that you can use debuggers in regular Python scripts anyway. So you can use the settrace even with PyTorch and tensors, which apparently there was an issue with TensorFlow previous versions, but now I don't know actually what's the state of affairs with TensorFlow. You guys will become experts in TensorFlow if you try it anyway. So yeah, so there are two advantages: automatic differentiation and GPU computation. Yeah. And tensors are pretty much mimicking NumPy arrays. So NumPy is the standard library for doing computing, scientific computing, and regular computing in Python. Yeah, Python is just a general purpose language, right? So if you want to use numerical or linear algebraic, problems, then you would use NumPy. So tensors are just trying to mimic them, but at the same time be able to push to GPU as well as do automatic differentiation. I would say, but there could be more features. You should go to the PyTorch website. Yeah. Any questions about this part? I think I'm a little bit delayed. So let's see. Okay. So we're already 50 minutes in. So let me quickly review CNNs and then we'll take a short break. Okay. Actually, we'll take a break in half an hour. I was thinking I was off. Okay. So let's quickly review CNNs. So okay, not this. This is not very okay. So generally you'll see diagrams like this. Okay, it's basically layers, and layers need not be always in this way where input is going to convolution layer and it's always going to a pool layer and so on. Sometimes a con layer is also followed by a con layer and then it's going to max pool layer, for example. Or sometimes there are skip connections. Okay, in for example in residual networks there are some connections going from some layers output to a layer which is not immediately succeeding it but like 2 layers down. Okay, things like that. But anyway, this is just an image of how the layers for a vanilla CNN look like. And if you really look at like here is another just a caricature of how a CNN would look like. So here is a image of a car. Let's say the first in this architecture there seems to be like 2 cons followed by pooling operation, 2 cons followed by pooling operation. So this type of 2 cons and then pooling is in architecture called VGG architecture, which was from 2014. It kind of was in the top 2, top 3 of the ImageNet challenge. Remember, ImageNet was this large scale visual recognition challenge classification. So in the classification task, that particular architecture was in the top 2, and then that had 2 cons followed by a pooling. Okay, so don't be confused why there are 2 cons and then a pool. You can mix and match actually, and there are now some best practice architectures anyway, like ResNets and so on. So here so what you're seeing is like some 10 filters, I guess. Number of filters is like 10. So we're just looking at the filters activations at each layer. Okay. Filters activations. Each filter, since there are 10 filters, each filter produces a 2D activation map, one slice of the output tensor. So think of the output tensor is having a depth of 10, and each of the matrix is just plotted as a figure. Okay. So what is this just trying to show that okay, some parts of the car are being captured at different layers, and then finally you have fully connection layer, which is going from the pooling layer to a five-dimensional score vector, and the scores are and the scores renormalized by the softmax operation look like this, with maybe the car being the highest probability and others being lower probability. Okay. And in terms of parameter counts, we didn't do this operation last time. I did say that there's a reduction in parameters because you see the same filter is being used throughout the whole image, and there are only few filters like that, right? So, for example, let's do a computation. If the tensor is like input tensor is 90 cross 90 cross 10, so it's somewhere in between the neural network. Okay, it's not at the entry. If it was at the beginning, it would be 90 cross 90 cross 3. Okay, depth RGB would be 3. Say the filters, and so the filters will have to have some width and height, but the depth of the filters has to be the same as same as the input tensor, right? So 10. And let's say we have 5 filters, and there's also a couple of choices that we need to make. How much we're going to push the filter in the spatial axis, and whether we're going to add padding to the input when doing the filter computation, like element-wise multiplication. So let's say stride is 1 and padding is 1. In that case, the output tensor size will be the same as the input tensor size. Okay, except for the last, yeah.
Sorry, what do stride and padding mean?
So it was about like sliding, right? So remember, so let's say my filter was 3 cross 3. Then first it would be somewhere over. So let's say padding is 0, which means that I'm not putting any cells around the input. So let's say this is the input tensor. Okay, it's 4 cross 4 here, 4 rows and 4 columns. Let's say my filter is 3 cross 3. Then it's when padding is 0, then it starts from here, and then a stride of 1 just means the next computation will be here. Okay,
So
just one row, sorry, one column to the right. Okay, that's stride of 1. Now you can do the same thing after adding 0 padding of 1, just means you're extending on all sides by 1 row. Okay, I mean I should put everywhere. So 1 row as in one row or 1 column. Okay, so it's like instead of 4 cross 4, now you have 6 cross 6 initial input, and then you don't start from the center, right? Then you start from at the top 3 cross 3 grid. Okay. So if you go to do stride 1 and 0 padding 1, then you get the same sized output. Okay, for a 3 cross 3 filter size. Okay. This is just a property, you can check it. I mean, this is not a big deal. I mean, nothing insightful here.
The padding is kind of like adding non-existent cells to it, more or less.
Yeah, adding padding is just for numerical. I mean, you may have some intuition that maybe the filter size is a little bit large, so it has to capture some pattern which may be at the edge of the image. or edge of the tensor, then you want to capture that, then you can add 0 paddings. I mean, it's just a convention design choice. Okay, you could zero padding means zeros. Yeah. Yeah, all three will be. It doesn't have to be RGB. It could be, it could be an intermediate tensor, so it will be all zeros. Yeah. Whatever the depth is, it could be RGB depth, which is 3, or it could be 10 here. So anyway, so as you can see, the number of parameters. So the output tensor is 90 cross 90 cross 5, and the number of parameters is the number of elements in each filter. So 3 times 3 times 10. That's the number of elements plus 1 bias. Okay, for each filter, and 5 such filters. So some number like this. But if you do a fully connected connection between 90 cross 90 cross 10 tensor and a 90 cross 90 cross 5 tensor, then you would have a huge number. Okay, 3 billion numbers of parameters. Okay, because every output neuron has to be connected with like 81,000 inputs. Okay, so there's no structure being exploited, and so that leads to a huge explosion in the parameters. Okay, any questions about this part? Okay, so I'm a bit slow here, but yeah, so backdrop, I will not talk so much about it, I guess, this time. Okay, so yeah, let's do the next thing, which is, as I said, we're going to look at 3 key things today. One is once we already have a trained model, how do we poke and understand it a little bit better? That's the first part. Second part will be transfer learning, which is where you will see that required grad and all that tricks are useful actually, because transfer learning is about reusing a pre-trained network and changing it for our task. Okay, for example, you can use an ImageNet based trained network like ResNet18 or something, and use it for classification like men versus women or dog versus cat or something like that. Okay, so it's a different task, but you can reuse the weights from which are trained from a different task, from let's say for an ImageNet task. And the third thing was using ideas like dropout and batch normalization to further improve the quality of the network in terms of output prediction accuracy and as well as training stability. Okay, those are 3 things. So let's start with the first one. So once you already train a network, there are a bunch of weights. Okay, each layer, each filter will have a bunch of numbers, and there will be many filters in your particular network. The question is, how do we understand what's going on? Okay, so what did the network learn actually? And so there are few attempts to understand what's happening. One is to look at the activations. Literally means like look at the take each image. Each image will produce activations. Remember, activations are the outputs at the each layer. So the output tensors basically. So we can just an output tensors. Typically they'll be 3-dimensional. So you can look at each slice of the output tensor, which are the activations, to see if they're catching some patterns are being propagated forward from that each image, each input image. Or you can look at weights themselves. So weights themselves are the filter weights, right? Each filter, if it's a 3 cross 3 cross 5 or 3 cross 3 cross 10 filter, then you can look at each slice of the filter to understand what is the filter trying to capture. So that is more like signal processing. I think we had we saw it in the previous lecture where I was sliding across somebody's face and there was a sharpening filter. So that was from signal processing. Idea that if the filter weights are such, then it will find edges or highlight the edges and remove the places where there is no edge. Okay. Anyway, you can look at filters themselves, and then the last 3 things are trying to understand. Is the neural network doing something sensible? One is if you have already trained your network, it's performing really well, doing really good classification. Then you can actually take each image and maybe not compute the scores, but compute the activations at the previous layer. Okay, and those activations are like high dimensional representations of I guess these are called embeddings. Okay, embeddings of the images, and then these vectors, okay, of the layer before the scores. Okay, the activations before the scores that you produce. If you embed them into 2 dimensions, you can see whether they're clustering. Okay, like for example, if it's cats versus dogs, maybe all the cat images produce vectors, which are the activations right before I compute the scores, if they're all close to each other compared to all the activations all these vectors for dogs. Okay, that's the third idea, looking at images in embedded space. The fourth idea is, if the network is actually detecting a cat, what happens if I occlude the cat? As in, like where the cat is present, I just change the pixel values to like zeros or ones or something. Okay, then the cat is not there. Hopefully the a prediction by the network has to be not cat, right? So that's like looking at the impact of occlusion, and and you can also look at uh, when does the so you can say when, like, what type of images trigger the trained network to produce a high score. For example, let's say that let's say cat is the first category or first class. So you want to ask, okay, given that I want to get a score of 1, what would the ideal image look like? Okay, maybe in my data set or a generic image. Give me the best image that will give me the first. So it's already trained. The weights are trained. All I'm asking is what is the input which will make the score, the first coordinate, the highest compared to everything else. Those are questions you can ask, and so those are the few ways to poke around with your CNN. Um, so actually, I'll skip this part. Um, yeah. So activation visualization is really not. I think actually first two visualizations are not. I think probably very useful. But anyway, so here is a visualization of. So input was a cat. We can't really see anything actually. But so the first conv layer had so many filters. How many? 1, 2, 3, 4, 5, 6. 6 times 6, 36 filters, I guess. So there is 36 layers in the output tensor for this case, for this particular CNN. And we're just looking at what cells, so what neurons got activated in each activation map. Okay. Maybe you're able to detect, okay, maybe this particular layer is responsible for detecting some pattern of the cat or some other pattern of the cat and so on. Maybe detecting edges and so on. And but if you do that at the fifth con layer, for example, fifth con layer would be some really long tensor of activations. Okay. In this case, there are like lots. Yeah.
If you're using filters, shouldn't the number of pixels reduce? Like it goes from a 10 to 10 to a 6.
These are activations. So yeah. So I'm not saying so it's basically the dimensionality depends on how big the filter is and how big the input image is. Okay, so the output tensor dimensions it can be computed given these two. Here we're just seeing the activations. Okay, so in this case we're just seeing after the first com layer we got some tensor depth. Tensor. We're just looking at slice by slice. It may give you some idea of so what idea it actually. Here the slide is trying to say that you can understand if some of the neurons are never getting fired. So for example, I pass one image, and then the remaining, let's say I had my data set at 100 images. I pass all the images and keep track. And then just focus on one, let's say one neuron here, and see that this never gets fired. Okay, in the sense it never becomes on. Okay, maybe that's a bad situation to be in, where the neuron is like, it's kind of irrelevant anyway because it's never. So when I said fire, it just means that it's never producing a positive output. Okay, it's because. I think I'm assuming that these are ReLU nonlinearities in there. So if the neuron is not firing, then maybe it's a dead ReLU in some sense. Okay, so the filter is dead. It's not really filtering and producing any output for any of the inputs. Like irrespective of what image I'm passing, the output of the filter is always black, as in nothing. Okay, so those are things that you can kind of debug. So I won't say much more about the activations. Visualizing activations is very difficult because first of all you will have a huge input images, huge number of input images, so it's time consuming. So you can also look at so you have the training model. Forget about the data. Just look at filters themselves. The problem is looking at filters is very non-intuitive. Maybe at the first layer it's somewhat intuitive because at least the first layer is interfacing with an image which has depth 3. So the each filter. Remember, filter will also have a depth something 3 in this case. You can, since the filter is of depth 3, you can think of that also as the image, and then you can plot the filter with all the 3 layers as a single image. Okay. So here you can see, and then at least the first layer we are saying that maybe the filters are detecting colors or some edge patterns like this and so on. Okay. But the problem is this happens with anyway, like irrespective whether you've trained your network really well or not well. So this is not very indicative. Yeah.
If you're looking at an output like that for your filters, and some of them are just random noise.
Yeah.
Is that, like, for example, I saw this really output with dropout, and those being dropped out filters or neurons with the random noise ones?
So dropout is only a part of the training. Once you've trained, you have the filters with all the numbers together. So we'll talk about dropout. Maybe you can ask me that question.
Yeah, I guess I've just seen this before, and I just had a lot of random
I mean, so thing is, so first of all, beyond the first level, it's kind of
Even on the first,
first level. Yeah, if they're noisy, then
would that be a bad thing or something?
no. I mean, so first level not being noisy or not very interesting patterns being detected means that maybe your network did not even achieve a good classification level. Okay, so I think bad performance and not detecting any low level patterns is a sign that yeah, you didn't do something well. But I think most neural networks, uh, the performance will typically be decently good, and then this is really not indicative of anything. Uh, yeah, I don't know. I'm not a practitioner. Okay, so the next idea is, as I said, the next three ideas are more about like understanding. Like this idea is about passing all the images through the train network, getting some activations. For example, uh, in this case, um, yeah, in this case, it's a yeah, I don't know why I even wrote this, but think of the activations will be output of a previous layer. So I'm just saying that you do a max of 0 comma the pre-activations of the previous layer. uh, let's call it little a. Then you compute these activations for all each of the images that you have, let's say 100 images, and then these activations will be whatever the dimension that you chose, right? It's for example the hidden layers. Remember the one hidden layer neural network, where let's say I chose the number of hidden nodes to be 1 or 10 or 100 or whatever. That will be the dimension of the activations. Then what you can do is now do a dimensionality reduction, project these activations back into two-dimensional, three-dimensional space, and then visualize things. Okay, so here is an example. So you can't really look at all the details of the images. You can get it from that website. Actually, that's from a paper. But what is being plotted here is the projected two-dimensional points of each of the image, and then instead of plotting the point, they're replacing that point with the actual image that appeared there, and then putting the images next to each other in a nice way so that it looks like a collage, really nice grid-like collage. Okay. And what they wanted to visualize is that, and the projecting is not by a PCA. There's some other nonlinear projection technique called TSNE. Okay, doesn't matter. It's basically projecting all high-dimensional vectors to a two-dimensional space in this example, and they're trying to see if like images of uh, similar things are in a similar cluster together. Okay, if they are clustered together in a low dimensional space in this 2D space, maybe they're also clustered together in the high dimensional space. Okay, which means that the network has learned even at the level of the scoring, the activation level, it has learned to kind of segregate them separately, like segregate the different classes properly. Okay, is that clear? So, for example, I can't see. So maybe airplanes are here, things like that. Maybe greenery is here. So they're separated and clustered together. And the next idea is occlusion. So to figure out like which part of the image is leading to a classification, to a class. Let's say if it's a cat or if it's a car, then which part of the image is actually making you classify it as that class. And so what we're going to do is the following. Let me explain by the first picture. This picture. So let's say this is my input image, and I want to say, okay, it's a neural network working fine. I've already trained the network, and now what I want to do is on this image, I want to say which feature of this image is letting me classify this thing as a Pomeranian, right? So what I'll do is start with a block of So what I'll do is delete pixels in this block of that original image, and of course, where do I do that? I'll do it everywhere. So I'll just like in CNNs, I'll start with a block which is at the top, delete those pixels, and see whether the classification is still Pomeranian or not. Move it, slide it one level, again check whether it's Pomeranian or not, and each level I'll have a number, whether what is the probability that it was classified as Pomeranian. That's this intensity here. Okay, that's this number here. This is the probability with which the class is equal to this. Okay, and you can see that as I'm sliding it through at each level, so this again becomes an image. Okay, it's actually not an RGB image; it's just an intensity map. So red color means high value and blue color means low value. Okay, and you can see that as I occluded this part or something, the probability of it being a Pomeranian has gone down. Okay, so it's picking up this part of the image to say that it is a Pomeranian. Okay, compared to other parts of the image. That's what this test is doing. It's something that you can do once you have trained a network. Okay. Same thing with this image, for example. I'm passing this grayscale thing left to right. I'm getting different probabilities of whether it's a car, car wheel or not. And if I start occluding parts of this, then it's not detecting it as a car wheel. It's detecting as something else, but I'm not focusing on what else it's detecting. I'm just saying what is the probability of a car wheel is going down as I occlude the wheel itself. Okay. And same thing with the right hand side example. Any questions? Okay. And the next trick is to figure out what is the most representative image which would make the score the highest for, let's say, the last the neuron which is at the output, or any neuron in between. Okay, so any neuron, basically if it's a ReLU type of nonlinearity, um, relative nonlinearity or maybe sigma nonlinearity, you can ask what value of the input, what type of image triggers that neuron, in the sense that that neuron value, the activation value is going to be high as possible, like maybe 10 units or 100 units or whatever it is. Okay, and so to do that, you can just do gradient descent. Okay, which means that you're not training the weights of the neural network. That's fixed. That's data for us now. Weights of the neural network is data. What we want to change is the image itself. So the image, which is the RGB image, like say 32 cross 32 cross 3, for example, I want to change those numbers and keep changing them such that the output at a given location is as high as possible. Okay. Now this is a computation graph, right? This is nothing but I'm trying to change some 32 cross 32 cross 3 numbers, given the weights are fixed, and passing it through and computing this number, and I can do gradient of this number with respect to the input image and do gradient descent, the opposite of gradient descent, such that I can figure out what's the best image that triggers this neuron. And here we are just showing, like, you start with a pretty much seemingly random. It's not really random actually. You have to start with some natural image pairs. Okay, it just means that it's not uniformly random picking a pixel value here. It's some slightly different trick. But if you do that, like, so in this example, what they did is they picked certain. I think in this case, maybe even the last 1000 class classification, where they pick the neuron corresponding to the gorilla class, and then just asking what type of images would be the ones which would trigger this the most. Okay, make the score the highest. Okay, and you can, I don't know if you can actually see anything. Actually, there are other pictures. Yeah. So, like, for example, here, this would be the ideal image which would trigger the goose class's neuron to be high as possible. For example.
What is the business for finding out factor?
What's the best image that's triggering your class, right? So the in your training data, it's detecting things, right? But hopefully, it's detecting the right things, right? So in this case, for example, you can say if the representative image for goose classes looks for some other patterns in the image rather than the goose itself, for example, whether it's next to a lake or something, then that means that that's not a production ready model. If you really care about that way. Okay. So these are all trying to understand these highly nonlinear models. Okay, you don't have to do these. Maybe if you're doing transfer learning, you'll probably not do these things. And then here, what they've shown is they picked random, some representative neurons and try to figure out what is the image that triggers that neuron the best. Okay, and these are some images. So I think at lower layers you will detect some simpler things, and at higher layers there's like a mixture of more complicated patterns. Okay. And instead of arbitrarily asking for any image that would maximize the output neuron, you can say what images in my data set are the ones which are triggering this neuron the most. Okay. For example, you can pick some neuron and say, oh, what images in my data set are triggering that neuron. So for example, this particular neuron in the first row is being triggered by these images the most. And the white box represents the what is called the receptive field of that neuron. Okay. So some neurons, so because the filters are only looking at parts of the input, and you change those operations. So the neuron, let's say at the third con layer, it's only looking at a part of the image. Okay, none of the neurons are looking at the full image actually. Okay, of course, if you go deeper into your neural network, that neuron probably looks at a larger region than the first filter. This is just showing like what the neuron is looking at, and these are the images which are triggering it to be high the most. Okay, this is just ways to understand your train network. Any questions so far? Is that too quick? Uh, so let's do the next thing, which is actually somewhat simple. So we can do that and take a break, which is transfer learning. Although it's simple, it's 90% of the work that you will probably do, but you will not spend too much time on it. So transfer learning is actually a very broad area. It's basically the idea of using information, using data from one application or domain, and building a model in that application and domain. For example, in telecom domain, okay, understanding reviews or call logs in telecom domain, and actually using it for like reviews or some other aspects in like energy domain or something like that. Like let's say in call center application. So transfer learning is big, especially because even for example, let's say you have two telecom vendors, maybe Sprint and Verizon, for which you're doing some data analytics task, and then this third client comes in, then you want to bootstrap their model better, then you can actually use the learnings from the previous models, okay, previous data sets. Okay, although Verizon and Sprint may be completely different from, let's say, Airtel or something. So let's see. So there are, yeah, and I guess on this slide, I'm just saying that very few people train neural networks from scratch, except for researchers maybe, and big companies. So typically, because there's a lot more bang per buck in not training the neural networks from scratch, but actually using pre-trained neural networks and deploying them in business applications. That's where a lot of value is there, and that's where you'll see a lot of blog posts and products on the internet. So there are two approaches. In fact, one approach is actually just a subset of the other. One approach is called feature extraction, and the second approach is called fine tuning. Okay, and let's start with feature extraction. It's a very simple idea. You have, in fact, we saw this in the embedding like visualization as well. What you do is you already have your pre-trained network, VGG, AlexNet, ResNet, or any of these networks. Okay, and actually Torch also has a pre-trained network, so you can just call Torch Vision pre-trained models or something. You can get the pre-trained network, which means that you get the weights from trained by other researchers, okay, like Microsoft or Google. So what you do is get the network. Okay, network is in Torch, for example, is just remember that was just an nn container, so nn.modules extension, whatever class, and so you can actually just delete the last layer of that last layer and the layer that is producing the scores. Okay, if it was, let's say, trained on ImageNet, it's producing a 1,000-dimensional vector, right? The last linear layer, it's going to produce a 1,000-dimensional vector. You can just delete it. Model.fc is none or something, or some such thing. Then what the model will do is just compute activation. So basically, let's say if the model is like this, you just drop the last fully connected or linear layer. Okay, then it's just going to produce activations. Okay, and instead of scores, and then those activations can be used as this activation vector can be called just a representation or an embedding of this image. Okay, and we saw this idea a few slides ago. This picture is just showing how, I think this is a picture of AlexNet, showing how they had the neural network, which had eventually like a 4,196 dimensional vector, leading to 1,000 class classification, 1,000 scores. Okay, this is from 2012, so a little bit older architecture nowadays. I mean, there are much more, I guess, slightly different architectures now. So anyway, ultimately you're going from an image, given the trained network, pre-trained network, just getting a bunch of activations, almost the penultimate to the last layer, and those are just the embeddings of the images. Okay, given the embeddings, just use okay, this is not needed. Just use the embeddings. Okay, just use the embeddings for as inputs to an SVM classifier or a logistic regression classifier, like a shallow model. Okay, so that's it. So the embeddings are now your feature vectors. 4,196 dimensional in that previous example case, and just use that as inputs to your shallow classifier. That's all. Okay, like even linear discriminant analysis, for example, and you'll be done. That's feature extraction, but that's too simple. So there's actually a slightly better way, especially if you have data. So in the previous example, you don't even, you do need data to train the logistic regression parameters or whatever linear model parameters. If you just do linear regression, for example, here also you'll need to train parameters. But the idea is to not think of the pre-trained network as a fixed feature extractor. Okay, so what you do is uh, train some of the layers which are towards the end of the network, not the layers at the beginning, because typically many images will have common lower level feature detectors at the beginning. So this common layer will have like edge detector, or circle detector, or things like that, and the layers above will typically detect more higher order complicated things that we saw even in the visualization, right? Layer 8 was like a multiple geese in the picture, whereas layer 1 was like just some small patterns. So what you do is, like for example, if it's an NN dot module, your model, which is an extension of an NN dot module, you just what you do is require grad for these guys to be zero. False, and require grad for some layers at the top to be true. Okay. In fact, the way you do it is nn.module actually gives you a function called model.parameters. Okay, model.parameters will give you the list of tensors that are there, and then you can just call dot required grad is true or false. Okay, so and then you just do the backprop. So the same you can do backprop to just learn. So if you do required grad is not true, so this part is become a feature extraction up to whatever this part is, and then the remaining part is going to be trained, okay, with some learning rate to change the. So you keep the same architecture as before, same loss function and so on. Yeah. For example, in this example, this part is frozen, and you're just changing the weights of the last two fully connected layers. You have to probably change the last layer to the task that you're doing. For example, you may be just doing a two-class classification, so you have to change that. So that's fine tuning. So that's all transfer learning means. You have trained it on some. So generally on ImageNet data, now you want to do it on your task. For example, classifying students versus professors, for example, and you can just do that by getting some smaller data and just fine tuning. Okay, or feature extraction. And here is an example to show that they're just showing. Previously the way image processing pipeline would look like. There will be image and there will be some feature extractors. There are actually domain specific workflows here. All these things, and then you do an SVM at the end after you do all the feature extraction. I don't even know some of the acronyms here, but compared to that, you dropped all this and directly did a CNN model. Now the weights of the CNN model can be used to do different tasks. In this case, maybe you're doing classification, but then once you do the classification, the same weights can be reused for some other tasks via fine tuning. Okay. Of course, you will have to change the loss function depending on the different tasks. You might have to even change some other parts of the network, maybe at the fine tuning, the last layers. But otherwise, everything else is, other weights are the same. And in fact, for example, for bird subcategorization, you only care about birds. You don't care about the rest of the classes, but you can still use the weights that are trained on other classes. Okay. And here they show that there is a big gain to be had by just reusing by just transfer learning. And just to, I showed you a lot of names here. Let's not worry about these names. I just want to disambiguate few key tasks. Classification is just identifying what's there in the picture. Okay, one of the 1,000 classes in image data. Classification, or actually localization, would be there is a class in there. There's a category as well as what are its bounding boxes. Okay, in what are the XY coordinates where the class is present. Okay, so that's localization. Object detection is multiple localization. So the picture may have multiple objects. So for detect each object. Okay, first of all, how many objects are there? Let's say there's an upper bound of at most 20 objects. Then for each object, tell me what the object is and what the bounding box is. Okay, and segmentation is a problem where each pixel is so you need to classify each pixel. Okay, so each pixel may be like background or part of dog or part of cat or part of duck. So it's like a pixel level classification. So this is like a too many classes. I mean, not too many classes, but too many things to be classified. Here, it's also a difficult problem compared to this one. Like the multiple potential, you need to detect multiple objects and figure out where they are. But there are actually pre-trained networks for all of them. So we'll see if we can use them. Some of you guys can use them in your projects if you want. Yeah, I guess the punchline is this is key for projects. Yeah, so yeah, let me skip that. I mean, I can explain the architecture, but I mean, all I wanted to say is that we saw con and then pool layer last time. Here, I'm showing you. I guess this is a clean architecture, to easy to understand. So this is a VGG net VGG architecture from 2014, and it has 19 layers. Okay, so about 5 pooling layers. You see max pools, and then 2 columns following each other. And I think these numbers represent the depth of the con layer. I mean, the number of filters basically. Okay, and I think they kind of use all 3x3 filters. Okay, all of them are 3x3 filters with stride 1. I don't remember with the zero padding and ReLU nonlinearity. So very clean architecture. I think these days are more, they have more things going on. So this is an example of it's a pretty good state of the art architecture from just 5 years ago. I mean, 5 years is a long time in this world, but still, and they were able to train this and get good performance. Anyway, let's take a break for 10 minutes and resume at 8:05.
So, if we are going to train a model, if we're going to transfer the learning, if the model is only predicting good and bad, and if we want good, bad, and neutral for the new data set,
Yeah.
is it possible? Because already the pre-trained weights are going to only detect good and bad.
Higher resolution? Yeah, you can. You can always go. You can.
So it will also predict the third.
Yeah, you have to change the. It will not automatically predict. You have to change the last weight matrix. It's producing the number of rows that it has is 2, good, bad. Now you want to change it to good, bad, and let's say something else. So now the last weight matrix has to be changed, right? Now it has to have 3. That's like saying I'm adding one more row to the weight matrix, like last one. Now, of course, the previous 2 ones have already trained. Now, if you had that labeled data, then you can actually train. I mean, literally keep everything else the same and just get the numbers for the last row if you want. That's the one thing you can do, but you can do more.
Yeah. As you were showing that image of the architecture of the VGG,